So this is our error term. The estimate is based on a simple fact that for positive x, 1 over x plus 1 is smaller than 1. As a result, to estimate the upper bound for the error, we may substitute the fraction in the integrand with 1. So the modulus of the error is less than the following simple integral, which is trivially worked out. This is the upper bound of our remainder term, valid for any positive lambda. But we can also make a stronger statement. We understand that as long as lambda is large, only small x are significant for the value of the integral. So 1 over x plus 1 is in fact approximately equal to 1 in the integrand. As a result, our upper bound for the error term is in fact its approximate value for large lambda. We have finally obtained the analytic expression for the error at large lambda. Let's recall that n here stands for the number of terms in the asymptotic series. Now we'd like to minimize the error term with respect to n. This way, we'll figure out the optimal amount of terms we need to take to get the best estimate for an integral. To find the extremum, we need to differentiate modulus Rn with respect to the corresponding parameter. But here, this parameter is discrete. It is an integer n. We can differentiate with respect to n composing the object drn over dn, where dn is equal to 1, but only if Rn is a smooth function of n. Here, Rn contains factorial. It's not a smooth function of n, but its logarithm is. So we take the log of Rn modulus and compute the derivative with respect to n. Lambda is large, we'll assume that the corresponding n is going to be large as well. Keeping this in mind, let's use the approximate formula for the factorial. It's a so-called Stirling formula. We'll prove it for you in the next lecture, but now let's just take it for granted. Next we plug it into the formula for the remainder and take the log derivative. And the result is as follows. This equation is easy to solve by consecutive approximations. By assumption n is large, so let's drop 1 over n term for now. As a result, n is equal to lambda. So the initial assumption is satisfied. Now let's find the correction. We represent n as a lambda plus some small correction delta n. Plugging it into our extremum equation, we get. Now we expand log in terms of large lambda and get the answer for the correction, delta n is equal to 1/2. So the full solution of the extremum equation is n is equal to lambda plus 1/2. Well, of course, the integer part of lambda plus 1/2 should be understood under this. Next, we plug it into our approximate expression for the error. And by the way, here's another very important observation provided by the Stirling formula. Once we have plugged it into the error function, we noted that the numerator behaves like n to n, while the denominator behaves like e lambda to n. So at large n, the numerator dominates over the denominator, and the error always blows up. This is just another proof of the fact that the series we studied diverges. So after some algebra and one more log expansion, we get the following approximate expression for the error. This is a very important result. We see that the error is unavoidable, but it is also exponentially small. And, by the way, it attains its minimal value at n of the order of lambda. Here, let me present the plot of error function once more. It was built for lambda is equal to 5. And you clearly see where the minimum is attained, precisely where we expected it to see. At n is equal to 5, which is nothing but our lambda. And the whole situation is unbelievable. We deal with the divergent series, yet we achieved an unprecedented exponential accuracy. For lambda is equal to 5, it takes just 5 terms. Now we are ready to draw our first conclusions. First of all, we realize that when dealing with asymptotic series, there is always an error term which never disappears. The best one can hope for is to minimize it by taking optimal number of terms in the series. In our case, the optimal number was of the order of lambda. The optimally summed asymptotic series represent the best approximation to the initial function. It has a special name. Such series is called Superasymptotics. As we remember, such series gives an exponentially small error, hence the name. So we can never put an equality sign between the function and its full asymptotic expansion. Instead, we write the wave sign. The wave sign should be understood in the sense that the number of terms can always be optimally chosen, and the series has unremovable minimal error for each value of lambda. That means that the accuracy which asymptotic series provides us with can't achieve any given in advance value. But in most cases, it's exponentially small and is more than enough. For example, our discussed asymptotic series can be written as follows. To get the superasymptotics, we should truncate the sum at n equal to the integer part of lambda. The superasymptotics becomes then a finite sum and reads. Finally, I give you the formal definition of asymptotic series from the book by Whittaker and Watson. Suppose we have a divergent series. Here is its first n terms. We denote this sum by In of lambda. They say that this series represents the asymptotic expansion of some function I of lambda if the error Rn of lambda function satisfies the following condition for a fixed n. Lambda is a seamed complex in general case. The error is just the difference between I of lambda and In of lambda. So this is the formal definition of the asymptotic series. Let's recall the error function we have encountered before. It is as follows, at large lambda, and indeed it works.